Have you ever wondered about how much energy does a bridge need to be able to run? Or perhaps have you ever wondered, can we produce energy as we consume it? The average medium housing electricity cost in England is categorised by day, month and year. So 1 day is equal to £3.20, 1 month is equal to £97, and 1 year is equal to £1,163. As we convert pounds to American dollars to get an idea of what the cost would be, 1 day is $4.75, 1 month is $143.85, and 1 year is $1,724.25. And an average medium house in England uses 21.6 kilowatts per hour. If we make a pause and try to compare it in Texas, 1 day is $4.40, 1 month is $183.30, and last but not least 1 year is $1,599.60. Now I am going to try to draw the bridge, so do not laugh. To open and close the bridge, lights, attractions, glass hallway, and all the other touristic activities, and powering the bridge up, it's worth 134 times more than a house. But how is so? Well, if the house uses 2,400 to 2,880 kilowatts per hour daily, then the bridge costs $636.50 daily, $19,095 monthly, and $229,140. Your goal is to reduce cost by at least 20%. It's been proved in labs. The method used to improve energy has exceeded 44%, but they are not cost feasible yet. For our calculations, we looked up commercially and cost-competitive products. The way we are doing this is by building on the road of the bridge a solar panel road. Said that, let's suppose we use the solar energy for 4 hours a day. So if $229,140 is a 100%, then 20% is X, and X equals $45,828. That's how much we would save yearly if we only use it 4 hours a day. We will be saving 21,827 billion kilowatts per hour.
Welcome to the Henry Ford's Innovation Nation. I'm Mo Rocca. Prepare to be mesmerized. Coming up, hitting the road for the ultimate power trip. Process of putting a plethora of parts in place, the cell signals changing your channels, and flying robots freaking out the flock. Next on the Henry Ford's Innovation Nation. Rarely are great game-changing inventions met with instant cheers. Usually there's first the chin rub, followed by the head scratch. I'm guessing that when the Wright brothers announced that they could fly, they were met with a bunch of, and then comes the head bonk. Of course you can fly. When we heard that a husband and wife team had invented solar roads, it was head bonks from the start. Here's Adam Yamaguchi.
Our sun is a huge ball of massive energy. And using solar panels, we can harness this power into electricity for residential, commercial, and industrial uses. Usually, solar panels are installed on rooftops in places where they are exposed to a lot of direct sunlight. But what if, aside from rooftops, we used other open spaces for solar panels? Areas such as parking lots and roads. Imagine the huge potential for generating more energy. Lucky for us, there's people already working on it. I drove on a regular asphalt highway to Sandpoint, Idaho to meet Scott and Julie Broussard, the creators of a company called Solar Roadways, to find out how they're working to turn parking lots and streets into power-generating boulevards crisscrossing the country.
How on earth did you guys come up with the idea for Solar Roadways?
Well, we met when we were 3 and 4 years old, and Julie's mom used to babysit me. And my favorite toy back then was a slot car track, a little electric road with electric cars. And my brainstorm as a little guy was if we could make real roads electric, then kids could drive.
That childhood inspiration eventually led to Scott and Julie's innovation: 6-sided solar panels that could replace asphalt road surfaces. The panels got the attention of the U.S. Department of Transportation, who awarded them 2 contracts to try and develop solar road panels that were safe for fast-moving vehicles, super strong to survive the weight of constant traffic, and able to generate power.
So this is the solar road panel.
This is one of 108.
So this is the thing that you were hoping to pave all of America with one of these
Exactly.
things.
Sidewalks, driveways, parking lots, airports, roads.
Can you walk me through a little bit of the technology that's
Sure.
inside here?
This is tempered glass, so it's really, really strong. It's 1/2 inch thick. It's textured on top. We had traction tested so it can stop a vehicle going 80 miles an hour on a wet surface.
And Scott's not kidding. I did everything I could to put a dent in the solar panel, but only gave myself sore feet.
The green part here is a circuit board. So we got the solar cells, the circuit board. On the circuit board are the LEDs for making road lines and graphics, whatever we need.
That's right. The solar road panels also contain LED lights that can light up in various configurations.
We can make any road line configurations, parking lot configurations. We can write verbiage, we can do graphics. On the underside of the circuit board are heating elements. So we heat up the surface so it doesn't allow snow and ice to accumulate. These panels actually talk to each other, so each hexagon has 6 neighbors, and there's a microprocessor in each one.
That means the solar panels are connected like computers. So if one goes bad, the other panels can report it, and the faulty panel can be easily replaced without expensive resurfacing or road closures. Other potential benefits include powering fiber optic cable lines and Wi-Fi hotspots through a cable corridor just below the road's shoulder. This corridor could also collect and recycle runoff from rain or snow coming off the solar panel surface areas. Covering roads with solar panels could help rebuild our nation's crumbling infrastructure, create jobs, and provide a charging network for electric cars.
Hiya everybody. I am back. We are about to study the road dimensions to see how many solar panels we would need to build to be able to cover the whole road. Here we have a length on 940 feet and a width of 60 feet, but when I mean the width, is referring to the roads of the bridge, not the height. So to find the surface area of the roads, we multiply 60 feet multiplied by 940 feet equals 56,400 feet circumflex 2. Then we have a solar panel with an area of 13.4 feet circumflex 2. Now we got to find out how many solar panels we would need to build the bridge. We divide 56,400 feet circumflex 2 by 13.4 feet circumflex 2, and we get 4,208.96. The Tower Bridge of London will need 4,210 pieces of solar panels. This is an example of how it would look if the project takes place. So we would need around 4,210 of these things, and they are not really that small. Edges are around 72 centimeters to be able to make it happen. Presents the materials and locations of materials inside the solar panel. The total cost of each panel is $938, and the total cost to build the bridge can be found by multiplying the total for each unit by the total supply needed. $938 asterisk 4,210. So that's worth $3,948,980.